This conference will now be recorded.
So today we'll be starting with a new chapter, Laws of Motion. This is fifth chapter in your NCERT textbook. So Deepa, I hope you are reading the book as well when I'm teaching you chapter by chapter. If you have any question anytime you can ask me. So today we'll start with a new chapter, Laws of Motion. So today's class will be first there will be a brief introduction about this chapter, what we are going to do in this chapter. Then we'll learn few things, Aristotle's fallacy, Galileo's experiments on inertia and laws of motion, Newton's laws of motion. So Deepa, so far what we have learned? We have learned and analyzed motion of objects. We have analyzed motion of objects, but we have not asked a question called cause. What is the cause of motion? We have never asked. Neither we have asked the details of the cause of the motion in the previous chapter. So that was actually the part of kinematics. Kinematics. So where we have analyzed the motion, we have seen the effect of motion and various other phenomena without learning the details of the cause of the motion, and the details of the cause of motion is the force. So what is the cause of motion? Cause of motion is force. That we have not discussed in the previous chapter. Okay. So we have seen in the previous chapter that when we need to discuss about uniform motion or object moving with a constant velocity, we need only the parameter velocity to describe its motion. Okay, only velocity we were requiring. Okay, but in case of non-uniform motion, we had to introduce the concept of acceleration. Okay, but still we had not asked about the force or the cause of motion. Okay, so in this chapter what we'll learn is the force, which is cause of motion, force or cause of motion, their details, and how force actually affect the motion, how various forces affects, I should write affect the state of motion. I should write state of motion of any object. Okay, so this is actually the agenda in the laws of motion chapter. Laws of motion means we'll learn various forces and how they act on certain object, and what is the effects of all those forces in the motion. Okay, motion or state of motion of an object. So this is actually the brief introduction about the chapter's overview or chapter's motivation. Now we'll ask the question, what is force? Why do we at all need? And we are seeing that the cause of motion is the force. Can we get some evidences? Yes, we can get evidences that we need some external agency to apply certain force or certain things to make an object move, or to stop an object which is in motion. There is force necessary. So we'll take up few common examples, like, see, if you have a football that is at rest initially, at rest, so does it move by itself? No. If it has to be moved in a particular direction, or if someone has to send that ball to goal, what has to be done? Someone has to kick it. Okay. In fact, to goal, to send it the proper goal or proper direction, an expert footballer can kick it nicely and send it to goal. So what you looked here, what you have observed here, kick. Okay. So this kicking is needed. Okay. Kicking is needed to make a goal. Okay. Otherwise, it will be at rest throughout. Okay. Now I'll show you another example. So this example, you look, in this in this actually a strong downstream is actually moving the boat full of these passengers. Okay. So here also, if you have a still water, will the boat move? No. You need downstream. Okay. Or flowing river, you need it, flowing river, to sail a boat. Otherwise, you need what? In the still river or still water, or if you want to go against the stream of the water, then what you have to do? You have to have an engine that we know. So what is the necessity of that engine? To give certain force to move against the stream. Or if you have a simple boat, you have to go downstream, and downstream gives the force to move it forward. Okay. Along with its stream. Okay. Or along its flow. So here also you can guess that there must be a force given by the stream on the boat to move it forward. Otherwise, it will be at rest. Okay. Then we can look this example. This is a nice example. You look, there are three skydivers. They are just having fun. What they do? They jump out from from helicopter. Okay. And they just freely fall. They freely fall down up to certain height. Okay. Up to certain distance. Okay. And then, like, this is before the parachute opens up. Okay. Before parachute opens up, the motion is actually free fall. So this free fall, why do these people come down? Why not going up? Why doesn't go up? Why always they come down? Anything in that matter, you just throw a substance, you look, that will come down eventually. So what is the so there must be something. Okay. there must be some force to bring it down. Okay, we'll discuss that. Now, the last example is this one. You look, see these nails. They are simply iron or steel made nails. They're attracted by this magnet. Okay, this is a magnet. It is attracted. So the nails are attracted. You look, there is nothing. There is no glue, nothing. So there must be a force, right? Or there must be something which is attracting towards it or pulling towards it. So you can see everywhere in every example you look, there is something, there is some, there are some external agencies, like, say, I'll just go one by one. So in this case, what is external agency which is giving a force? External agency, you must be aware of this agency. Agency is the source of the force. So here external agency is the leg. Okay, leg, or the man itself, you can say, footballer. Okay, footballer, that is the external agency. Okay, now what is the external agency over here? That is the stream of the water. Okay, this is the external agency to provide the force. Okay, we'll just go to some examples. So what is the external agency over here? That is the gravity. So gravity, okay, so gravity is actually giving the force, so which is in terms of weight. Okay, in terms of weight, the force act on these people, and they are really falling, because other than gravity, there is no force on them in ideal situation, but there will be air resistance, etc. So those things we'll see. Air resistance, when they are coming down, air will be actually giving some force to them also. So I think we'll learn it later. So there will be some buoyancy forces due to the fluid here, the air. So that we'll learn later. So this is the weight which is bringing them down. So this is actually the force, and the agency is, external agency is the gravity. And look here, magnet has magnetic force. Okay, it applies magnetic force to attract these nails. And in fact, last two examples, look here. See, these are in contact, I understand. But what about this? These are not in contact with the magnet. So agency can, so external agency. So what we have learned? So we have learned that external agency is required. So first point should be, force is the cause of motion. Okay, cause of motion. Then second thing is that external agency provides the force. So I said leg, hands, or air flow, or maybe gravity or magnetic force. So these are actually external agency. So here in this case, the magnet is the force provider. Okay, and one more point is, external agency can be in contact to apply the force. Agency can be in contact to provide necessary force, or external agency may not be may not be in touch sometime, okay, to provide a force. I'll just explain these last 2 points. Okay, external agency is providing force, that is very nice, but they can be either in contact or without contacts also. External agency can apply force like gravity. Gravity is actually everywhere gravity is there. Okay, no need to have touch with any body or anything. So you always you are under gravity. Okay, without any touch, you don't even feel. Okay, and another point is this one. You look, see, these are in contact, I know, but what about this? These are not in contact, but still they experience a force. So this is actually the last point, that external agency, even without in touch also, can apply force. Okay, can apply force. And see the previous examples like football, anything you just throw out, throw up, or anything in that matter you want to move or want to set a motion in that, you need by just giving a hit. Okay, so those are the examples where external agency is actually touching the object to set a motion or to provide a force. Okay, so this is simple example, these are simple examples to give you an idea about force and how the force is required to make a motion in an object. Now what we'll do, we'll see these are the points which I have already discussed. But the question is whether a body is needed to apply a force to keep it in a uniform motion. So we have learned in the previous chapter that uniform motion means uniform motion means an object is in motion with a constant velocity, constant velocity. Okay, so this is a very good question, and this was initially answered by, this question was initially answered by Aristotle. And according to Aristotle, a constant and continuous force is required to keep a body in uniform motion. Okay, so this statement, actually this is called Aristotle's fallacy. In the very beginning of the mechanics, classical mechanics, Aristotle had given his ideas about motion, and specifically he had stated this thing, that a constant and continuous force is required to keep a body in uniform motion. So you might be thinking that this sentence is, and this, see, this idea is, or concept is really true. If you want to have a motion in object and that to continue with a constant velocity, you must be providing external force continuously, and a constant force has to be given. Okay, so this is called Aristotle's fallacy. Okay, fallacy. But unfortunately, this fallacy was proved to be wrong, and that was done by Galileo. Okay, so see, in any case, when there is a theory or any science is being developed, this must be having a nice history. This is actually the part of history, that the very beginning, in the very beginning, Aristotle, Galileo, they have contributed, they have put their thought process and ideas to develop the mechanics. And then thereafter, after Galileo, Newton has taken over the lead role to develop the classical mechanics. Not only that, he had given a lot to the scientific community. Okay, all right. So he was one of the genius scientists, physicist, mathematician, everything. He had contributed in mathematics also. The whole calculus he had developed. The initial, so whatever we learn in 10 plus 12 and other places also up to graduation maybe. Okay, so Galileo had actually done various experiments on inertia, various simple experiments on mechanics, on the motion of objects, and then he actually proved this Aristotelian fallacy to be wrong. What was the fallacy? Fallacy was that a constant and continuous force is required to keep a body in uniform motion. That means to have a body moving with a constant velocity v or constant velocity anything in for that case, you need to have applied a constant and continuous force throughout the motion. But Galileo had proved that to be wrong. We'll see from which experiment he had proved that to be wrong. So Galileo had done nice and simple experiments. First, let us look these experiments. So there are three experiments you can see. One is motion of an object. This one, the first one is actually okay. I have, I think. So motion of an object moving down the inclined plane. So motion of an object. So moving down inclined plane. Okay, moving down inclined plane. The second is an object moving up. Okay, moving up the inclined plane, moving up the inclined plane. And the third is actually an object moving on a horizontal plane. Horizontal plane. So we learn what are these three representing. So Galileo concluded from the first experiment that when an object moving down the inclined plane, it is actually getting accelerated. It is accelerated. Okay. When the object is moving up the same inclined plane, it is actually retarded. Retarded. Okay, it is actually retarded. Retarded means its motion is actually being stopped, or you need to apply certain force to have the upward motion. Okay, and the third thing is again interesting. So this is actually accelerated motion, this is retarded motion, and what about this? This is a neutral motion, neither accelerated nor retarded. Okay, when an object is moving with a uniform velocity on a horizontal plane, it is neither accelerated nor retarded. Okay, we'll see this motion, uniform motion on a horizontal plane is actually equivalent to the state of rest. The state of uniform motion is equivalent to state of rest. We'll learn why. Because in case of state of uniform motion, there is, see, this is uniform motion, no acceleration. Okay, no acceleration or no retardation. Okay, when there is no retardation or no acceleration, there is no force involved in that. Okay, so from this experiment actually he could conclude that if there is a, see, if the floor on which this motion is happening, if that is perfectly smooth and there is no opposing force called friction, okay, friction, if there is no friction, then you need not require to apply any external force for an to an object which is undergoing a uniform horizontal motion or uniform motion. That means if a body is moving with an uniform velocity or a constant, with a constant velocity, does not require to apply a force which was suggested by or stated by Aristotle, that you need a constant and continuous force to stop, sorry, to have have a uniform motion of an object. But from this experiment, Galileo could actually give a hint that we do not require to apply a continuous and constant force on the object which is moving in moving in a uniform, like with a uniform velocity, to keep its motion on, okay, or to continue the uniform motion. So only there is, if there is any force which is actually opposing the motion, in that case you have to apply certain force to cancel that opposition force, okay, opposition force. In this case that opposition is friction. So we'll see, he had done another set of experiment, okay, from where he could establish this fact more strongly, that if an object is moving on a horizontal plane with uniform velocity, you need not apply any force to keep its motion on, okay, or to continue a uniform motion. Object needs not be applied a continuous and constant force on it. Okay, let us see what is this experiment and how he had concluded that. So in this, actually, you look, the first one, this is the first one, this is second one, suppose, and this is third one. So the first one, there are double inclined planes. So this is one inclined plane and this is another inclined plane. So from one, see, in one case the object is actually moving down, and in another case the object is actually moving up the inclined plane. Okay, what we have already learned here. So in the same inclined plane, this is called double inclined plane, double inclined plane. So in this case, what it is done, actually, you look, what is done is that an object is taken to the top of this inclined plane and just released from there. Okay, so as soon as it is released, it is coming down, okay, and crossing all the way, coming to the other inclined plane. It is, so it is actually moving down and it is going up to the inclined plane. Okay, and one good thing is that if this double inclined plane, it is smooth enough, then the object in the other inclined plane goes up the same height as the initial height was. Okay, so suppose this is actually 5 meter, okay, 5 meter height, it was released from 5 meter height, then on the other inclined plane this object will try to go up to the same height, that is 5 meters, okay, on the other inclined plane. All right, if this is really smooth. Now look, if the slope in the second case, slope of the same inclined plane is being little bit reduced, okay, look, the slope is reduced, this is more steeper, the slope is more. So in this case, once you release from one of the inclined plane, it just goes up to the other inclined plane, and eventually this time also the object will be actually reaching to the same height as the initial height, but in this course of so in this case, look, this is the distance it traveled in the previous case. Now it is some extra distance he has to, like, this object has to travel to reach up to the same height as the initial height. Okay, now look what was there in the second. There was reduced inclination or reduced slope. Sorry, this is reduced slope. But the third case, if the slope is 0 itself, okay, slope is 0 itself. That means the, see, this is called actually an inclined plane. The other side is actually the plane. So see, this has zero inclined plane. That means this is horizontal plane itself. Okay. So in this case, if you just release from the inclined plane, it starts moving along the plane of this, and it goes up to infinite distance if there is fortunately no frictional force or opposing force on this smooth plane. So it will try to reach up to the same height, but it cannot, because here is zero inclination, there is no inclination, and because of that it has to move infinite ideally to have this, to have reaching like to reach this height. Actually it will try to reach the height, but since there is no inclination, so it will move for infinite distance, okay, without a stop. This is an ideal case. Okay, ideally. So what is the idealized case? Ideally, an object moving on a smooth or frictionless path with uniform velocity an object moving on a smooth or frictionless path on with with a uniform velocity moves forever. It will go infinity, moves up to infinity, or it can move forever if you go with time. So, but in physics there is no infinity. That means there is no idealist situation. We live in this real world where fortunately we have, fortunately or unfortunately, there will be friction. Okay. So look, in this case, what is the outcome of these experiments is that you need not require, you need not require to apply an external force to continue a uniform motion. Okay, uniform motion of an object. Okay? To have a uniform motion of an object, you need not require to apply an external force. Okay? Alright? So uniform motion, look, what does this mean again? The uniform motion and rest, state of rest, oh, state of rest actually are equivalent. I'll explain this. Equivalent. This will again be able to understand when we learn the laws of motion given by three famous, like given as three laws by Sir Isaac Newton. So first law, second law, and third law. So you look here in these experiments somewhere or somehow or other, one thing is very clear. If we just discuss this part, state of rest and uniform motion. What are the similarities between them? So what is the external force on this? Rest means there is no motion, so there is no force at all. So what about uniform motion? It has a constant velocity always in the motion. So in this case also, since there is a constant velocity, there is no acceleration, so no force at all on it. This also. So in case of uniform motion or in case of state of rest, in both cases there is no external force applying on the object. So this is the equivalent. This is the equivalence of this rest and uniform motion. Okay. So in case of state of rest or in case of uniform motion, there is no external force applied on object. Okay. So in this case, you can see when there is no force applied on this object which is moving in a smooth plane, will go like it will move for infinite time. Okay, or for infinity. Sorry, for so it will go up to infinity or it will move infinitely long time before it comes to rest. Or in case of, okay, so in case the object is at rest and no force is acting on that, the object will remain at the same place. If you keep a book on a table, it doesn't move by itself unless you apply a force. So this is actually giving you the knowledge of inertia of object. So that is a property of object. Property of object of any object is that is is not to change, not to change its state of rest or motion. State of rest or motion. State of rest or motion by itself, unless, so by itself, unless compelled by any external force. Okay. So what I tried to mean here is that any object has a tendency to keep its state of rest or motion intact. Okay, it does not like to change its state of rest or uniform motion by itself. Okay, So this property is called the inertia of objects. Inertia. Inertia actually does not allow any object to change its state by itself unless it is compelled by an external force. Okay, and Galileo proved that because of inertia, an object which is in uniform motion, it will continue its motion up to like forever. It will continue its uniform motion forever if there is no external force acting on it or compelled it to change its states. So in that case, if the object is moving on a horizontal plane, and if that plane is sufficiently smooth to make the frictional force ideally zero, then that object will move forever by itself, and for that you need not apply any external force. Okay, so this is what he had told, that for a uniform motion you need not apply a force. Okay, but whereas Aristotle told that for a uniform motion of an object you need to apply constant and continuous force. Okay, so that was flawed. Flawed in the sense that was proved wrong by Galileo from this series of experiments on inertia of objects. Okay, now we'll just move on to Newton's first law of motion, and we'll try to understand what it is and how it is containing the message of the inertia, or it contains motion, sorry, inertia of object. Okay, look here, everybody everybody so this is the statement of the first law, Newton's first law. Everybody continues to be in state of rest or uniform motion in straight line, uniform motion in straight line, unless compelled by some external force to act otherwise. So this is the first law, and the statement itself, you can understand this is containing the message of the inertia itself. Okay, okay, let us see. In this case also it is relevant to discuss about force. Look, when I say there can be two situations when there is no force. So look, when no force on an object, acting on an object, what does this mean? This means the net force is zero. Net force is zero. Okay, but again, what does this mean? This means that the acceleration is zero. Acceleration is zero. If the force is zero, that means change in the velocity is zero. Change in the velocity is zero. Okay, that means v is constant. So from here you can understand, when an object is moving with a uniform velocity, then there is no force. Or in other words, we can say if there is no acceleration, then there is no force. Okay, if there is no acceleration on an object, there will be no force acting on that. I will take up few example here. See, suppose you have a book. See, whenever I say there is no force, that doesn't mean that there is no force. There is no force acting at all. Actually, there can be a set of force. Okay, set of forces are acting on that, but the resultant or the net force might be zero. Look here. See, in this case, the book is actually at rest on the table. In this, a book is at rest on the table. Okay, so you might be telling from first law of like Newton's first law that said if the book is at rest, then force must be zero. But here you need to understand that this net force acting on the object is zero. But if you say no force is acting on the object, then it is wrong. Okay, then it is wrong. How? I'll tell you here. See, there is always gravity which is acting on each and every object on this earth. Okay, okay. So this book is resting on the table means what? Obviously, weight is actually, see here the weight is always acting on the downward direction. So suppose this is the book. Okay, so this is the book. Okay, this is the book. So the G, so weight is actually m into G. We learn it actually in the second law. So this is the weight which is acting downward, and see the book is touching the table, touching the table. It is not just going into the table, okay, or it is not it is not fly, like the book is not flying off the table also. Okay, so in this case mg is working, like it is acting downward direction. So then there must be another force which is acting exactly opposite in direction. Suppose this is f, then this will be in minus f. What will be the resultant? This will be zero. So resultant will be zero. To make the resultant zero, we say that there is a force which is given by the surface on which the book is resting. So the surface of the table also gives an opposite force, that is called normal reaction. What is this called? Normal reaction. Okay, normal reaction. And this normal reaction is actually given by the surface of the table to the book exactly in the opposite direction, and the force is exactly equal in magnitude of that weight. Weight is mg, so this will be exactly equal to r, the normal reaction acting on this book, and that is provided by the surface. So when you just stand on the floor, in that case also you have to understand that the normal force is given by the floor through our feet, through our feet, so that it is actually balancing the gravity or gravitational pull towards the earth center, which is in form of weight. It is actually just getting like balanced by this normal force. Okay, and see here we always say that the object is not moving up or not going down. This book is not going up nor going down. This is because of the normal force. Okay, this is because of the normal force, because normal force is acting exactly opposite, and this is actually gravitational force. Okay, so when any object lying on a table, we must be saying that there must be two forces, gravitational force and normal force. That's why it is not flying off the surface. Okay, another good thing is, look here, when you talk about the motion of an, so here basically we are just learning about various forces. Okay, so in this case, look, a car is moving on the road. When it is it is with uniform motion, we need not apply any force to continue its motion. Okay, but eventually in reality we'll see after coming, see if you just have a car moving with uniform velocity and just leave it like that, see after some time eventually the car will be at rest. It will come to rest. Why? Because there is friction, and that friction is acting against the motion of this car. Okay, so friction generally arises, we'll learn about friction again. So friction generally arises in the contact surface. Okay, contact surface, and that force actually an adjustable force. Even this normal force is an adjustable force. If I just keep another book on that, okay, still it will not fly off or it will not go into the page. Okay, it will balance. So earlier suppose the force was 5 Newton. Okay, 5 Newton. If the gravitational force suppose, okay, 10 Newton suppose. So earlier it was 10 Newton. Okay, 10 Newton. Now when the weight becomes more, then the normal force becomes more. Suppose it is 50 Newton down, so then R also will be 50 Newton. So this is called self-adjusting force or adjustable force. Adjustable force. Adjustable force. Even frictional force is also, static friction is called adjustable force. Okay, static friction. So while we read, we'll just keep a single class for the friction itself. That is very, very important, interesting, and also a little bit complex to understand. Okay, so when the car is moving uniformly, then also we have to apply force in this case to keep it in uniform motion. Why? Because there is a friction, and to overcome that friction you have to apply force. Not, it is not because of because of making the car move with uniform velocity, but to cancel the effect of the friction. Okay, you need not apply any force to make an object move with uniform velocity or constant velocity. Rather, you have to act, you have to apply a force against the gravity. You have to apply a force. So if this force, and suppose this is capital force, and friction will act always in the opposite direction of the motion of the object. Okay, so this is F. All right, so we have learned what is friction little bit, and we have learned what is Newton's first law of motion. First law of motion says that. So actually it is containing the inertia part. So what is the outcome of Newton's first law? Okay, that is inertia. That's why this law is called law of inertia. And the inertia is actually, the mass is the measure of inertia of any object. Mass is the inertia, is the measure of inertia. Measure of inertia. Okay, measure of inertia of an object. Okay, okay, so I'll just give you a brief introduction to the inertia, and there are, see, classifications of inertia. So inertia, there are two types of inertia. One is inertia of rest, and second thing is inertia of motion. I'll give you simple example, by that you will be able to understand. So what does this inertia means? If some object is at rest, it will try to be at rest unless you apply a force. Suppose there is a box. Okay, full with full of books in your room. Unless you give a push, okay, it will not move by itself. Okay. So this is actually state of inertia. There is a simple and very interesting example. Okay, I'll just first take state of, just a minute. Yeah. So look here. This is a nice example. Sometimes we see as a magic. Okay, and magic always stands on science. Look here. If you take this demonstration, you can do at home. So this is a card. Okay, you can take postcard or maybe a playing card also. You take a 5 rupee coin, place on it, and you can do one thing. You can just place it on a glass. Okay, on a glass, and let it be nicely placed, symmetrically placed. Okay, and put this 5 rupee coin on the middle. Okay, at the middle. Now if you just give a sudden force to this card, what will happen? Actually the coin drop, and this drop here in the glass, whereas your card will fly off, or it will just move forward. Okay, so this is actually the, like, one of the famous examples of inertia of rest. Inertia of rest. See, initially the coin and the card, this card, they both were actually at rest. Okay, they were at rest. Now when you are applying a sudden force to this card, what happens? This will have an acceleration. Okay, or it will have a motion. It will just move forward with certain velocity. Whereas the coin, since it is done at a stroke, that means it very like very the time of application of the force is very very short. As a jerk, you just give it as jerk, very, for a very short time. Then since since this coin was at rest in the beginning, it will just try to keep its state of motion intact. It doesn't want to change because of inertia, because it was at rest initially. So it will try to keep itself at rest, but there is no card to rest on, since because of since the card has actually moved forward because of the sudden jerk or sudden force applied to that. Okay, so that's why this is called like inertia of rest. There are many such example you can pick up from textbook, or maybe from your evidences also. See, I can give you another example that is also a very good example. See, when we clean the, actually when we clean the rags, okay, which are used in winter season, okay, to cover ourselves. Okay, so those things are actually sometime gets lots of dust. So how to clean them? Just take a stick and then beat it. So when it actually flies off, the dust will not fly off because of the rest, like inertia of rest. I can give another example of inertia of rest. That is when we ride bus or any vehicle. initially if the bus is at rest and then it suddenly starts running, what happens? Our body actually moves behind. Why? Because initially we have the car at rest along with the floor where our legs are, okay, where we are standing. So the whole system was at rest. But when the car started moving, the floor of the car also started moving. Then what happens? Our legs or the lower part of the body, which is in contact with the floor of the car or the bus, that starts moving, but our upper part of the body will be remaining at rest still. That's why that happens. I'll just give you an example of inertia in motion or inertia of motion, and then we'll conclude. Later we'll take up this inertia again little deeper. Okay, so let us see the other example. This is actually inertia. This is the second case. Inertia in motion. This is inertia at rest. Okay, inertia, sorry, inertia of, this is inertia of rest. This is inertia of motion. I hope explanation is not required from this figure itself. You can understand when an Ola driver, he is actually riding, maybe he is actually uh, driving the car some 80 kilometer per hour, okay, with such speed. And when there is something and he has to stop the car, suddenly he applies brake. And then what happens? His upper part of the body goes front. Why? Initially the whole body along with the car was in motion, but when he applies brake, the lower part which is in contact with the car comes to rest. But because of the inertia of motion, the upper part of the body still in motion. So it will go forward than the lower part. So that's why this happens. Okay. So I'll stop it here, Deepa. Uh, here this class was almost an introductory class, not very mathematical in derivation point of view. It was very simple and mostly philosophical class. So if you have any doubt or any question you come across about this point, so whatever I have discussed, or maybe you have for a long time, you can ask me. Do you have any question, Deepa? Deepa, do you have do you have any question? Okay, if you don't have, then I'll stop it here. But you are always welcome. If you want to ask any question anytime, you can ask me. Okay, I'll stop it here for today. So bye for today.